This is lecture 3C for Calculus 1. It is on 2 rules for differentiation and on taking the derivative of polynomials. In the previous lectures, we found derivatives either by drawing secant lines and taking the limit of the secant lines as they approach the tangent line, or we took the limit of the difference quotient. Every time we would want to take a new derivative, we have to start again and go through the whole process. There is an easier way. And to find this easier way, we follow the same method as we did for limits. In limits, we found the limit for some very simple prototype functions. Then we combined that with some limit laws, and we were able to take the limits of very complicated functions without having to start over from first principles. With the derivative, we do exactly the same thing. We take the derivative of certain simple prototype functions. Then we have these derivative laws. We combine these simple prototype derivatives and the derivative laws to take the derivatives of very complicated functions. So I'm going to start with the 2 derivative laws that we need to know right now. The first one is a constant multiplier rule. Here is the rule. If I take the derivative of a function f that's multiplied by some constant c, I can just put the c out front and take the derivative of f by itself. And here is the proof. Okay, the proof relies on this result from the limit. If I take the limit of c times some function, then I can just, this is c times the limit. Assuming the limit was L, then the limit of c times f is c times L, its limit. So we're going to use that. So first, to take derivatives, we rely on taking the limit of the difference quotient. So here is the derivative. Here is the limit of the difference quotient. Okay. Now, if I want to take the derivative of c times f, I have to do the same thing. But if I'm multiplying the function by c, this term up here has a c in it, c times f of x plus h, and then here's c times f. The c's can be factored out. Now, using this law right here, the c can come out in front. When c comes out in front, this is just the derivative of f, and we've established the law. So the idea is a constant multiplier rule. If I take some function and I multiply it by c, try to take its derivative, it is as though I took the derivative and then multiplied by c. The next rule is the addition and subtraction rules for taking the derivative. And here are the rules. If I have 2 functions f and g, and I add them together and I take the derivative, it is equal to taking the derivative of f and adding it to the derivative of g. Okay. So the proof of it, here we have the derivative of f plus g. Again, we have to use the difference quotient. But we can rearrange the difference quotient. Okay, I can put everything that pertains to f together and everything that pertains to h together, and then separate it out as 2 fractions. So here is f of x plus h minus f of x over h. Okay, and here is g of x plus h minus g over h. Okay, now for the limit laws, if you're trying to take the limit of 2 things that you're adding, you can take those limits separately and add the results. So the limit of the first term is the derivative of f of x, and the limit of the second term is the derivative of g. So now we've established 2 laws, the constant multiplier law and the addition or subtraction rules. In essence, we have established the linearity of the difference operator. And now we are going to establish the derivative of a very simple prototype function. This will be the power function. And here is the rule. I'm going to say that the derivative of x raised to any power n is n times x raised to the power of n minus 1. In other words, the n comes out in front and the exponent decreases by 1. Okay, so here's the proof. It's a little messy, but it's not bad. So I'm taking the derivative of x raised to the n. So here's my x to the n. Of course, I have to have x plus h to the n right here. So now I have established the difference quotient. I'm going to say that n is real, and I'm going to rely on the binomial theorem to expand this first term, the x plus h to the n. It's pretty easy to extend this to arbitrary exponents, but let's just rely now on the binomial theorem. Okay, so if I expand x plus h to the n, I get all these terms. X to the n, the next term is x to the n minus 1 times h. You can just work through the binomial theorem and you will get this. All right, it's standard. I'm subtracting x to the n from it. Obviously, the x to the n's cancel off. So this is gone, and this is gone. So what I'm left with are all these terms. Notice that each one has an h in it. I'm going to split them up as separate division problems. So here's this term. I'm going to split this up like it's divided by h here. Okay. Then I'll take the second term, and I'll write this right here, also divided by h. And I keep going down. Here's my linear term in x anyway. I take that term, I divide by h, okay, fine. And then I had, this was my last term, h to the nth power. So I have h to the n divided by h. On this slide, I have written once more the final line from the previous slide. That's why this is so you don't have to look back or try to remember it. Okay, what I had before was the derivative of f with respect to x equals a limit as h goes to 0 of the difference quotient. By working through the binomial theorem, subtracting off the x to the n's, they fall off of there, and I'm left with a bunch of terms all involving h. I break each one out separately. Each one is divided by h, and here I have it here. Now, in this first term, obviously, these h's right here, this h and this h are going to cancel. Okay, fine. That gives me the first term, n x to the n minus 1. All right. Now look at this second term. I have an h squared here, and I just have an h in the denominator, so I end up with an h in this answer. I'm going to keep going like that because as I go down in these terms, the power of h in the numerator is going to increase and increase and increase. So here's the last term. Well, this one next to the last is h to the n minus 1 divided by h. Okay, I end up then with h to the n minus 2. Remember, same base, and they're divided, subtract the exponents. Okay, the last term, I have x to the n divided by h, no, h to the n divided by h, sorry, gives me h to the n minus 1. Okay, so now look at all these terms that I'm taking the limit of as h goes to 0. This first term right here has no h. All the others have h's. As h goes to 0, all of these guys turn to 0. They're gone. And all I'm left with is this, and that was the result. If I take the derivative of x to the n, I get n times x to the n minus 1. The n comes out in front, and the exponent decreases by 1. Now I'll just use this to take the derivative of a constant. I could write the constant as c times x raised to the 0 power, right? Because x to the 0 power is 1. So I'll take the derivative, which means I'm taking the derivative of cx to the 0 power. Okay, the c comes out in front by the constant multiplier rule. By the rule for x to the n comes out in front. In this case, the 0 comes out in front. The x becomes x to the minus 1. Well, 0 sends everything to 0, and the result is 0. If I take the derivative of a constant, the answer is 0. So here's a summary and some examples. Okay, if I take the derivative of a constant, the answer is 0. So if I take the derivative, for example, of the number 4, the answer is 0. If I take the derivative of x to the n, the answer is n times x to the n minus 1. Okay, over here, for example, I'm going to take the derivative of x to the 19th. Well, the 19 comes out in front, and x decreases to 18, or the 19 decreases to 18 in the exponent. So the derivative with respect to x of x to the 19th equals 19 times x to the 18th. I'm going to skip down here to this rule. This is a rule that combined the constant multiplier rule with the rule for addition and subtraction for derivatives. And this is the rule, I combined both these, showing the linearity of the derivative operator. So I have d by dx times alpha f plus beta g. So this is the equivalent of multiplying the function by a constant, alpha or beta, and then adding or subtracting the functions. The alpha and the beta come out in front, and all I have to do is take the derivative of f with respect to x and the derivative of g. So I'm going to go up here. I can get rid of some of this yellow stuff. Okay, what if I take the derivative of a, some constant times x to the n? Well, the a stays the same because it's a constant multiplier. The n comes out in front, and the exponent becomes n minus 1. So here's an example. I'm going to take the derivative of 5 times x to the 8th. Well, the 8 is going to come out in front and multiply the 5, give me the 40, and the exponent of 8 turns into 7. If we want to apply this to more than one term, here we go. The derivative with respect to x of 12 times x to the 6th minus 3 times x to the minus 2 equals, I'm going to get a 72 because the 6 and the 12 multiply together to give me the 72. The 6 then turns into this 5 because it decreases by 1. In the second, I have a minus 2, it multiplies a minus 3, and I get a positive 6, but the minus 2 decreases to minus 3, and there's my answer. So, what we've established here is that we have a couple simple rules, and we have the derivative of one simple prototype function, which is x to the n. By combining all those rules, we can just use them. We had to establish the rules by using the limit of the difference quotient, but now that we've established the rules, we can just use the rules, and in these cases, we don't have to go back to the difference quotient, at least for these examples. So we can now take the derivative of any polynomial. Here's an example. Well, no, here's a polynomial just by itself. The derivative with respect to x of the polynomial in general, a to the n for the coefficient, x raised to the n for this first term, the leading term. The next term I'll say a to the n minus 1, and x raised to the n minus 1, and so on till I have a1 times x, and then the constant is a0. By the addition and subtraction rules for the derivative operator, I can take the derivative of each one of these little things separately. So that's what I've done in the next line. Okay, well, so I take the derivative of the first term plus the derivative of the second term plus the derivative of the third term, and so on down to the derivative of the constant. By the constant multiplier rule, the a to the n comes out in front, and I just have to take the derivative of x to the n, and I know what that is. So here's that result. The n came out in front, the a to the n is still there, then you have x to the n minus 1. Go to the next term. The a to the n minus 1 is still here. It's a constant multiplier. The n minus 1 comes out in front. Here we go, multiplying that, and the n minus 1 turns into n minus 2. Go to the next term. The a to the n minus 2 is a constant multiplier. It just sits there. The n minus 2 comes down, there you go, and it turns into n minus 3. Now the linear term, the exponent on the x is 1, so you have 1 times a1, but then 1 minus 1 is 0, x to the 0 is 0, so you just get the constant. You only get the constant because the derivative of x is 1. Now when you take the derivative of a constant, you get 0. So let's see this in an example. So I'm going to take the derivative of this polynomial, 14x to the 35th minus 2x to the 22nd plus 0.3 times x squared plus 20. So I just have to take the derivative of each one of these separately. So the constant multipliers, they just stay here. There's the 14. Here's the 2, actually the minus 2. Here's the 0.03. I take the derivative of x to the 35th, the 35 comes out in front, the 35 turns into a 34 because it decreases by 1. This 22 comes out in front, multiplying the 2. The 22 turns into a 21. Now here, the 2 comes out in front on the squared term. The 2 turns into a 1, which is invisible and I don't have to write it. And the derivative of the constant 20 is 0. Here we're taking what looks like a the derivative of some fractions, but we can apply the same rule. Instead of x4 divided by x to the fifth, I can write this as 4 times x to the minus fifth. And instead of 1 over x cubed, I can write this as x to the minus 3. Okay, now I just go ahead and take derivatives. The minus 5 comes out in front. It multiplies the constant multiplier of 4. And minus 5 decreases to minus 6. Okay. For the next term, the minus, you still have your negative sign. The minus 3 comes out in front. But minus 3 decreases to minus 4. So you get minus 20 x to the minus 6 plus 3 times x to the minus 4. So in summary, we established the linearity of the differential operator, meaning we can take the derivative of anything multiplied by constant. The constant can come out in front. Or if we add two functions together, take their derivatives, it's the same as taking the derivatives separately and adding them together. Okay. Now, we established the derivative of one simple prototype function, which is x to the n. Putting all that together, we can take the derivative of polynomials. And we can even take the derivative of any function, any algebraic combination of power functions. Because we can take the derivative of each little term by themselves, right? Any constant multipliers just remain in front as constant multipliers. If there's an exponent on the x, that exponent comes out in front and then decreases by 1 as an exponent. So with these two rules, all kinds of things become very easy to differentiate.